Maths of the Coronavirus Part 6, R values. Let's revise from our first video. We started off with one person sick, and then we assumed that this person made two other people sick. There and there. And then the next day, when the virus spreads again, each of those makes two other people sick. There, there, there and there. And those four people make two people sick in turn. And we get a total of 8. Excuse my rubbish drawing. So if we start here, we have one person sick there, then 2 people, then 4 people, then 8 people. So that's day number 0, day 1 of the spread, day 2 of the spread, day 3 of the spread. And in that first video we said we could figure out how many new people were sick out here on, say, day 10 by looking for the pattern. And the pattern is that it was 2 to the power of the 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so forth. So if I want to know how many people or new people will be sick on the 10th day, it's 2 to the power of 10, which is going to be a very big number. Now that's what we looked at in the first video. Let's have a look though at this 2 at the bottom and see what happens if this number here changes. Well, first of all, what would cause that number to change? Well, to make that number change, this would have to happen. We start off with a sick person, but instead of making 2 people sick, this person makes 3 people sick. And then each of the people that she's made sick, in turn, makes 3 more people sick. Now, I'm not going to keep drawing that tree because the number of branches gets really big very quickly. But look at the pattern again. We start off with one person sick. Then it's the first day of the spread, we get 3 people sick. On the second day of the spread, we get 9 people sick. And so when I go to do my powers, so that's day 0 of the spread, day 1, day 2, my powers are going to be 3 to the power of 0, because anything to the power of 0 is 1, 3 to the power of 1, which is 3, and 3 to the power of 2, which is 9. So you can imagine that the next one would be 3 to the power of 3, which is 27. And if you want to figure out, in this case, how many people would be sick on the 10th day, it would be 3 to the power of 10, which if you run that through your calculator is 59,049 people, which is an awful lot of sick people. Now in class, you will have seen things like this, where we have 3 to the power of 4. And you've seen this number here referred to as the base, and this number here referred to as the index or power. When we talk about the spread of diseases, this number here tells us, as you've just seen, how many people get made sick by somebody. So on average, one sick person makes 3 more people sick, or 2 more people sick, or something like that. And in the study of the spread of disease, that number is called R-nought, or R0, depending how you pronounce that. And what that means is that if nobody in the community has any kind of immunity, that is, anybody can get the disease, and there's no social distancing and there are no protections in place, how many people can somebody who is already sick make sick? How many people can they pass the disease on to? And that would be R-nought. Now you might think to yourself, well, if they're sick, they could just keep passing it on and keep passing it on. But remember, when you get sick, one of 2 things happens eventually. Either you get well, which is the best outcome, or you die, which is obviously the worst outcome. Either way, you can't pass the disease on anymore. So there's only a period of time during the illness when you're contagious, when you can pass the disease on. And during that time, the average number of people you could pass it to is called R-nought. And in the case of maths, that R-nought becomes the base of your exponential expression. Let's have a look at what that looks like in terms of disease spread. I've got a little animation here for us. I'm going to start not with one sick person, but with 1,000 sick people. So, for example, if 1,000 people were let off a cruise ship that had the disease and came out into the community, let's see how quickly the virus would spread. Well, we look over here to this slider and we can see that our R-nought is 2, which means every sick person, on average, makes 2 other people sick while they're still contagious. And here I can just slide up the days. So on day 1, as we'd expect, there are now 2,000 new sick people. Day 2, that's become 4. And you can see the disease, the blue thing, spreading in the middle. By day 7, the entire population of the little town I live in, called Coffs Harbour, is now infected. If we take it up a few more days, by day 13, the entire population of Sydney, which is the capital city of the state I live in, is now infected. If I go further again, it only takes 2 more days for me to infect the entirety of Australia, which is a somewhat scary rate of infection. Let's take it back down to our day 0. So there's our 1,000 people coming off the cruise ship, and change our R value up to 3. So on average, every sick person is making 3 people sick. Now, we'll go up through the days and we'll see the rate of spread. And now it's spreading extremely rapidly. It only takes 10 days to exceed the entire population of Australia. Here's the same information on a graph. You can see the R value at the bottom. There's the 1,000 people on the left. And coming up through the days, you can see how the number of new sick people increases, and the shape of the curve created by joining the dots is that characteristic exponential curve. You can take it back to 0. This time I'm going to bring it up to an R value of say 4, and let's have a look at how quickly this disease is going to spread. So by day 5 I've exceeded my entire town's population of disease, and that's with an R-nought value of 4. Think about what it means to have measles with an R-nought value of something like 12 or 15. But remember I said the R-nought value is how many people are infected by a sick person if there's nothing to stop it happening. If nobody is already immune to the disease, if there's no social distancing, if there's nothing else to prevent it happening. And so if my R-nought value, for example, is 3, and I start with my 1,000 people on the cruise ship, then every time the disease spreads, say it's spreading once a day, I multiply by 3. And then for the second day of the spread, third day of the spread, I just keep multiplying by 3 all the time. And then you can figure out using that how many people are newly infected on a given day. But let's assume we've actually done some work to prevent the virus spreading. Now we introduce a slightly different concept, because we no longer have R-nought, as in there is no immunity in the community. That's what the nought means. There is no immunity, there's no protection in the community. We've actually changed it to not this rate of reproduction of the virus for no protection, but the rate of reproduction if there is some protection. What's referred to as R-e. That is the effective rate of reproduction. Sometimes it's RT. That is, what is this number here if we start to protect people? Let's say we've reduced it from 3 to 1. And let's see what happens to our 1,000 people. Well, it doesn't take very much maths to figure out what's going to happen here. I start with my 1,000 people who have the virus coming off my cruise ship. But each of them can only make 1 person sick. So we multiply by 1, which is 1,000. And then we multiply by 1, and then 1. And as you'd know, it doesn't matter how many times you multiply by 1, the number 1,000 isn't going to change. So while there will be 1,000 new people sick each day, the number's not actually going to get any bigger. It's just going to stay flat at 1,000. Let's go another step further and take our R-e number, our effective rate of reproduction, that's what the R means, reproduction, and let's change our R-e to be a number that's less than 1. So let's take 0.75. Now if you've got a calculator handy, grab it and follow along here. So you've got 1,000 to begin with, and then we multiply by 0.75. Now that's going to give you an answer of 750 because that's 3/4 of 1,000. Now the next day we're going to multiply by 0.75 again. So just grab your calculator and go 1,000 times 0.75 times 0.75. And that's going to give you 562.5. Now 562.5 is a bit silly, you can't have half a sick person, so we might make that 563 if we were rounding that up. But you get the point. You take your initial number of sick people and times it by this R-e number as many days as you like. And let's have a look back on our animations, what that does to our virus. So this time I've assumed we're part way through the epidemic. We've already got the blue circle number of sick people out there. But now our social distancing is starting to kick in. You're staying at home, you're quarantining yourself, you're doing all the right things. And our R number, which is now R-e, is 0.7, anything less than 1. Let's see what happens as the days go by. The number of new infections shrinks. And eventually, if we go far enough, the number of new infections will go to 0. It's easier to see on the other graph. So I've reset this graph to our 1,000 people coming off the cruise ship, and I've set our R-e to 0.75. And let's see what happens as the days progress. The number of new people made sick is decreasing. And if I stretch that graph far enough to the right, that will actually become 0. And so once we get to that point, nobody else is getting sick. And all these people that were made sick in the past, huge numbers of those are going to get well. And so the disease will die out. In basic maths terms, what you're looking at is exponential equations. So again, this slider will give you your R value, R-nought or R-e. And have a look at the red line. While my R stays above 1, I get very rapid growth. That red line climbs extremely quickly. Once I get down to 1, exactly 1, I have a flat line. So if I have an R-e value, the base of my exponential expression of 1, then my disease is flatlining. If I go below 1, then I go from exponential growth to exponential decay, where you can see it starts high, but then it drops off very, very quickly. So now you can see how mathematics and exponentials, particularly changing the base of an exponential in what's called an R number in the study of the spread of diseases, helps us understand when we have gotten on top of the virus, when we are going to start seeing the curve flattening and this thing starting to die out. I hope it helps you understand what's going on.